This is the most inclusive course on cotton fiber to fabric quality and manufacturing. It reflects more than 30 years of experience by one of the top scientists and utmost experts in the field of cotton research and textiles. Please be aware that what you will see is only very small pieces of some parts of the course. This course is over 40 hours in total. As you will see, the course uses direct teaching by the speaker, slideshows and real videos of all processing from harvesting and ginning to spinning and weaving. The course comes with all videos and hard copy of slideshows. An e-copy of one of Dr. Elmogahzy books also come with the course. Again, these are only few clips. A complete course should be ordered via Amazon.com using the title, the author, and the code number of the course.
The first part of this course is an introduction of critical concepts of fiber to yarn engineering and cost optimization. The second part deals with fiber characteristics such as fiber fineness, fiber length, fiber maturity, fiber strength, neps, and cotton stickiness. The third part deals with yarn characteristics such as yarn count, twist, strength, irregularity, and imperfections. All characteristics are discussed in the context of measurements and impacts on fabric quality. The fourth part deals with fiber processing, starting with harvesting and ginning and going into cotton mixing and blending. All stages of spinning preparation including opening and cleaning, carding, drawing, combing, and moving are covered in great details. Different types of spinning such as ring spinning, compact spinning, rotor open-end spinning and friction spinning. The course will also cover effects of yarn and fiber characteristics on textile fabrics.
As we mentioned in the previous session, ring spinning being the oldest spinning system, the most conventional one, has some limiting factors. We mentioned the limitations associated with the speed, with the production rate, with the fact that we are using a rotating element, which is the whole package mounted on a spindle, the limitations associated with the need to drag a very small piece of metal, a C-shaped metal that we call the traveler, around the ring at very high speed, and the frictional heat and the wear out of this piece. All of these limitations have contributed to the stimulation of developing new spinning systems. And this whole trend began in the perhaps in the late 50s and resulted in the introduction of the rotor spinning in the mid 60s, maybe in the latter part of the 60s, 1965, 67, Indeed, in 1967, the rotor, or the first commercial rotor spinning machine, was introduced. And the idea of rotor spinning, which is the first technology we're going to talk about in this session, was to first dispense the roving process. Recall that the roving process was is an essential process prior to ring spinning, where we reduce the size of the drone sliver down to a very small fiber strand that looks like a yarn, but it exhibits a very small twist. It's also very thick, that we called it the roving. With the rotor spinning system, there is no need to feed a roving. Instead, we can go straight from the drone sliver to the spinning process. The other issue was to actually be able to make a large package instead of the very small package that we've seen in the ring spinning, which is the small bobbin, that to be able to immediately produce a large package on the spinning machine. And by doing that, we are eliminating another important process, which is the winding process. So two processes elimination represented the main attraction of rotor spinning. Now, if we add to that the fact that the rotor spinning itself operates at much higher speeds than the ring spinning, then we are talking about a complete economical package that has attracted textile technologists and textile manufacturers in the 60s and until today to use rotor spinning. As we mentioned in the overview, rotor spinning was first commercially introduced in 1967. It was based on breaking the fiber flow for the sake of a higher speed twisting, meaning higher rotational speed and then higher production speed. It was based on separating the twisting and the winding, which is a key limitation in the ring spinning, the fact that both twisting and winding, as we mentioned early, in ring spinning are interconnected or associated with one another, limits the possibility of increasing the rotational speed and increasing the production. And more importantly, now we have a rotating element that is a very small rotor. This piece of metal we see here is a very small rotor that doesn't carry a package like the spindle in ring spinning. Instead, it carries a few fibers inside the rotor wall, and this allows a very high speed. To give you an idea, the spindle which carries the bobbin in ring spinning can operate today at maximum of about 23,000 RPM. That small rotor in the most modern machines can operate at more than 150,000 RPM. Recall what we mentioned early in spinning preparation, that in order to prepare a fiber strand for spinning, we begin with an opening and the cleaning process. Also involved a lot of blending between different fibers, different fiber bales. Then we go to the carding process. After that, we have a drawing process, perhaps one or two drawing passes. And then we go to the roving process to make a ring spun yarn via ring spinning. The alternative to that was to take the drone sliver directly to one of those new technologies of spinning, either air jet or rotor spinning. that to make a carded yarns. We also mentioned that we can make a combed yarn via the addition of the combing preparation and combing. And again, after drawing, we go to roving to make ring, or we take straight from drawing to rotor and air jet. So you can see here that in comparison with ring spinning, the benefits of using rotor spinning is that we are eliminating a whole process here, which is this one here. This has been eliminated completely. Okay, now after spinning, in this case we have a winding process where we can make a large package, right? Now this winding process in case of rotor spinning has also been eliminated, because rotor spinning, as we will see shortly, indeed produces a large package. In some cases, especially the people that produce fine yarn, and they use very long stable fibers, they indeed go straight from the carding. They use some of their waste fibers to make coarser yarn on rotor spinning by going straight from the carding to the rotor spinning, as you can see here. So that involves the elimination of drawing as well. So one can see here that rotor spinning can indeed result in some economical benefits and the cost reduction associated with that. These are key issues of rotor spinning to begin our discussion. Here we see the drone sliver feeding directly to the rotor spinning machine, and the points to be kept in mind at this point of time is that we are producing a larger package. You can see the packages. You will see here it is, but you will see it even better in the video clip that I will show it to you in a minute. Now let's take a look at this video clip here and see firsthand how a rotor spinning looks like in practice. Here notice the larger packages, as you can see here in the top, and the spinning box or the rotor box, which is, of course, you cannot see the details of it. We'll show it to you in a minute, but the machine is basically fed by a card or drone sliver. You can see those cans here, and that is the input material, and the output material is the large packages. This high-speed operation that dispenses the roving as well as the winding is also associated with a great deal of automation. The carriage that you see going around the frame, patrolling every rotor head, indeed acts as a piecer. It pieces the yarn if it breaks. It also cleans up the rotor box in case of trash accumulation, and in addition to all of that, it also does the packages. Once again, here is the rotor spinning frame. Here is the patrol carrier, which goes around and detect any breakage in any one of the rotor head, and does the piecing, does the cleaning of the rotor head, and also does the doffing. It's an amazing robotic system that you hardly see any operators walking around the machine to maintain or to take care of anything. This is a very self-activated system. So not just that we dispensing processes here, the roving as well as the winding, but we're also dealing with a fully automated process. Here is the piecing action in as you can see it here, where the yarn is being pieced. Also, you will see later on in other video clips the cleaning action. Here is the winding head, and you can see how large this package is compared to the small bobbin that we have seen in the ring spinning in the early video clips. Major development, as you can see here. It's very important to keep these points in mind. Now the question is, do these developments come at some expense, especially the expense of quality? This is what we will discuss as we go into the principle of rotor spin. Before we get into the principle of rotor spinning, let us just recall some of the important features of the traditional or conventional ring spinning. And as I mentioned earlier, these are the continuity of fiber flow from roving to yarn, and continuity, as we indicated before, means no disturbance of the fiber flow. And if you don't disturb the fiber flow, then the fiber orientation will be kept. Indeed, it will improve as we add drawing during ring spinning. The other issue that we discussed in association with the ring spinning is the tension control, and we've seen the balloon shape of the ring spinning, and how this balloon shape and how the tension distribution has contributed a great deal to the quality of the yarn and ring spinning. The migration phenomena, the compactness as a result of the centrifugal force on the balloon. Also, we discussed the development in ring spinning represented by the compact spinning system, which produced almost a hardness-free yarn. And we also mentioned the true twist as a result of the fact that we have no disturbance in the fiber flow. Also, as a result of the fact that we have tension control. As I said, in order to apply a good mechanical twist, we have to hold one end momentarily, and we have to rotate the other end. And if we can achieve that tension control, then the twist will be a truly twist, and that gives us the option of controlling the level of twist. Indeed, as we will find out very shortly, this is one of the reasons why ring spinning survived all these years and still going very strong in areas such as knit apparel fabrics, for example, where you want both low twist and reasonable or acceptable strength. It's a combination that only ring spinning can produce, and at a very wide range of yarn count. Now we talked about. Now we go to talk about the open end. Well, or rotor. As I said, rotor spinning is commonly called open-end spinning. So if you hear me saying open-end spinning, that still implies the rotor spinning. And as I mentioned earlier, in the principle of spinning, I like to put this under the category of interrupted spinning. And we're going to talk about the interruption of fiber flow very shortly. This is a general view of the rotor spinning machine. What we are feeding here is a sliver, as you can see, and we know that the sliver is a very large fiber strand that may have 20 to 40,000 fibers per cross section, and we feeding it to an opening roller. And as soon as you see an opening roller, as I mentioned in the overview, that immediately gives the indication of some disruption of the fiber flow. Every time there is a mechanical penetration through the fibers, then there is disruption.